Greetings, peeps! We're back discussing torque and static equilibrium. First of all, what is torque? Okay, torque is a force that causes rotation around an axis of rotation known as the fulcrum. That's the pivot point for a system in rotation. We also need something called a lever arm. So it's the force perpendicular to the lever arm. Well, what's the lever arm? Let's take a look at a little drawing over here, a little situation. Well, over here is the fulcrum, right there. There's the fulcrum, the pivot point. And we have this rigid body. That rigid body has a force applied to it at the end over here that's perpendicular to the lever arm. The lever arm being this length over here. I kind of prefer looking at it from this perspective. Your book talks about the line of action, but I prefer it this way only because the force could be at an angle. And if the force is an angle, it's easier to do the trigonometry, and I think when you analyze what the angle of the force is, that's perpendicular. So we just try to go back and work at it so that we say, oh, okay, this is the force that's perpendicular, and here's the lever arm. Together, they produce rotation measured as Newton meters, okay? So the torque has a unit of newtons times meters. We've seen newtons times meters before when we talked about work. However, work has been we use the unit of joules for that. We don't use Newton meters, and it actually is quite different because in that case, the force is parallel to the displacement. In this case over here, we have a force perpendicular to the lever arm. So they're actually quite different things. Even though they look like they would have the same units, they mean very different things. And we just call this a Newton meter. That describes the amount of rotation around a certain axis of rotation known as the fulcrum. What are the conditions for static equilibrium? For balance, we want things to be balanced out. Well, the first thing you need is that the sum of the torques equals 0. That means that your torques clockwise equals your torques counterclockwise, so that all your rotations are equal on one side to the other. Therefore, you've got some equilibrium that way. You also need the sum of the forces in the y direction equals 0, sum of the forces in the x direction equals 0. In other words, you need equilibrium, an equal amount of force up and down. That's force up equals force down. And you need also forces that would be equal left and right. So left equals fright. Don't be frightened, it's just the F right, okay? It's not really fright. And this is the situation over here. What we're gonna do is a couple of examples using a seesaw and a big kid and a little kid, and we're gonna figure out, hey, if the big kid sits on the seesaw, where does the little kid go in order to balance it out? You'll recognize just from your common playground experience, assuming that you've done the seesaw, that if you have people of different weight, you need to position yourself away from the fulcrum, which is generally at the center, in order to keep balance and have a dandy old time bobbing up and down, okay? So we'll figure out how that works, and that actually will work right into the calculations that you'll need to make for your hanging mobile. All right, here we go. I now feel like the Green Lantern. This is so cool. Check this out, I have superpowers. Okay, here's our situation. I really don't have superpowers. I just know physics. Uniform seesaw. Uniform seesaw, what does that mean? Is it wearing a uniform? Does it have a tie or something? No. A uniform seesaw just means that the mass is distributed evenly along the material. So if it's wood, you can imagine that the wood is pretty much going to be the same, give or take a few knots, whatever. But we have a uniform plank for our seesaw. Mass is evenly distributed, and that mass is 10 kilograms. And it's 2 meters long, and the fulcrum in this case will be at the center, at the 1 meter location. So what I've done here is created a drawing of the seesaw. We're at 0 meters here, 2 meters here, and here's the middle, where we've got the force of the weight of the seesaw. And of course, in a uniform object, the center of gravity, where all the weight actually acts, the balancing point of the seesaw, if you were to balance it out, would be at the center, okay? So here's the center of gravity, and it happens to be right at the fulcrum. So our center of gravity is right at the fulcrum, which means that if the lever arm of the center of gravity is at the fulcrum, the lever arm is 0. There is no lever arm. Therefore, the seesaw itself does not produce a torque around a pivot point because the center of gravity and the pivot point can be different. And we'll do a situation like that next. So we're going to do the simple case where the center of gravity is at the pivot point, the fulcrum right there. Okay, big kid stats. His mass, or her mass, who knows, just a kid, big, 50 kilograms at position 0.6 meters. So I've kind of set up a coordinate system where over here at the left is 0 meters, and over here at the right is 2 meters. This is the positive direction. So 0.6 meters from this point over here is where the big kid is going to sit. And that means that the big kid actually is a certain lever arm distance away from the fulcrum. And that distance away over here is actually going to be 0.4 meters. 0.6 plus 0.4 is this 1 meter distance over here along the plank from the end to the fulcrum. The little kid's mass is 30 kilograms. We want to figure out a couple things. What position is the little kid to balance out the seesaw? Where are we going to put this guy? Well, it's going to be to the right of the fulcrum because we need that balance. But right now, the big kid is producing a rotation around the axis like this. So if I were to draw it out, that rotation would be in the positive direction this way, trying to create a counterclockwise torque, like that. Therefore, we need some balancing torque clockwise in order to equal the situation out. All right. The other thing we would like to determine is the normal force acting at the fulcrum or on the fulcrum, supporting the weight of the kids in the seesaw. So in other words, we've got weight pushing down the big kid. We've got the center of gravity of the seesaw pushing down, and we've got the little kid pushing down. Something's got to push up to balance it out. Forces up equals forces down, and that's the normal force right here at the fulcrum. So, you know, oftentimes it's a little post or something like that where the bar is. So right here is a force known as the normal force that's pushing down, or rather pushing back up because all the weight is pushing down on it. So all that, this piece of structure right here is responsible for supporting all that weight. So how do we do this? Part A. Well, let's take a look. We'll go with the torques being equal first. So we have the torques clockwise equals torques counterclockwise, like that. And therefore, what do we have? Well, let's go with the torque counterclockwise because we know something about it. We've got force big times lever arm big. So I'm going to write it down like this. Force big times lever arm big. Okay, that is the only force creating a torque in the counterclockwise direction. And so that equals the forces, the torque clockwise, and that's created by the force of the little guy times his lever arm or her lever arm. So we have this L over here that we're trying to find, actually, solve for that. Okay, so what we have here is force little times lever arm little. And the thing that we want to solve for is actually this guy right here. So this is like super easy, guys. This is so easy. You're gonna love this. This is great. So here we go. I'm just gonna solve this for this over here, lever arm little, because that will tell us this distance over here, and then we can tell what position we are relative to the origin. So here we go. We have L little equals force big times L big divided by F little. So all I did here is isolate lever arm little divided by force little, and we get this expression over here. It's pretty easy. Now I can be a little bit more sophisticated. I can write this as this equals M big times G times L big over M little times G times, that's it, because it's just F little. Check it out. Look at what cancels out when we want to calculate the position. So we actually can cancel out G. We can cancel out the gravity. Therefore, we don't even have to calculate the force. We could do that. We can certainly multiply the mass by the acceleration due to gravity to get the weight of the big guy and the weight of the little guy, but we don't have to. We can just take the masses straight up. So it's this ratio that we're developing over here. So we have now our moment is to plug in the numbers. So L little equals mass of the big guy, 50 kilograms, times L big. L big is this 0.4 meters. Remember, it's the lever arm distance, not the 0.6 meters, but the lever arm distance away from the fulcrum. So that is times 0.4 meters divided by 30 kilograms. Like so. All right. So what does this equal? And again, that's the lever arm distance. So we got 50 times 0.4 divided by 30. And I get 0.67 meters. And that would be over here. So what that says is he's going to be further away from the fulcrum than the big guy. And that makes sense, because what we know about torque is that if you're less weight, you need to move further away to equalize the torque. So the lever arm distance is 0.67 meters. All right, so that's definitely further than the 0.4 meters, which means that this guy will be at position 1.67 meters, like that. All right, so that's part A. Part B is really simple. We have all the masses. We add those masses together, multiply by G. That's it. So we just have the force normal is equal to G times mass big plus mass little plus mass of the center of gravity of the seesaw itself. And what we have is, let's see, 9.8 and 50 plus 10 plus 30. Oh, we'll call that 90, I think, yeah, 90 kilograms. All right, and so what do we have here? We have 9.8 times 90 and 882 newtons. Boom. All right, next example we do will be a little bit more complex in that we're going to shift the center of gravity. I'm going to try to roll through it a little quicker since we have the theory. I'm just going to kind of bang it out for your edification and enjoyment. But here we go. Seesaw solved. Position 1.67 meters for little guy and 882 newtons for the normal force. Right on. Hey now, peeps, our situation is slightly different now. We have our uniform seesaw, the mass is still 10 kilograms, the plank is 2 meters long, but now we've moved the fulcrum from 1 meter to 0.9 meters. So we've shifted it away from the center of gravity of the plank. Our questions are the same, our kids are the same. What position is a little kid to balance out the seesaw? What's the normal force acting on the fulcrum? So the situation is a little more complex. Let me point it out. Now we have the pivot point, our fulcrum right here. This is position 0.9 meters. So the big guy is still at 0.6 meters, but now the lever arm distance has changed. It is no longer 0.4 meters, it's just 0.3 meters away like this. And the only torque that's being created in the counterclockwise direction is still the responsibility of the force of the big guy. Now though, we have two torques to balance out that one. The two torques over here are created by the center of gravity. So the actual weight of the seesaw, where its weight acts is at the center of gravity, and its lever arm distance is only 0.1 meters away, plus the torque created by the force of the little guy and we want to determine what this lever arm distance is away from the fulcrum so that we can then figure out what position the little guy is going to be at. What's your prediction? Is the little guy's position going to be more than the 1.67 meters it was before or less? I want you to think about that as I run through. Part A. Well, we have a similar equation from before. Still, our torques clockwise equal torque counterclockwise. All right, let's start with the counterclockwise over here. We have force big. This looks the same. So we have force big times lever arm big, creating that counterclockwise torque. And now it equals two terms. We have the force of center of gravity, that's the plank, times the lever arm of its center of gravity away from the fulcrum, plus force little times lever arm little. So it's still a very, very simple algebraic solution. We just have one additional term. Well, SADMAP, we're going to subtract this term away and then divide. All right? So what I actually have over here is that L little, and now I'm going to skip a step. We noted before that because each of these terms has G in it, I'm just going to divide by G, and it's really a system of looking at the masses. Now, if I asked you for the torque, then you would absolutely use G. You would go mass times gravity times the lever arm, and that would be the actual value of the torque in Newton meters. But to find L, every one of these terms has a G, so it cancels. All right, so we can divide out by G in every case. So here we go. Our solution here is that L little would equal F big times L big minus, because we would subtract this to the other side, actually I can go M, I'm sorry, because like I said I was going to do that, we're divided by G, M COG times L COG, okay, divided by the mass of the little guy. All right, now let's plug in our numbers. So this equals, all right, we have M big, 50 kilograms. Lever arm distance is 0.3 away. How do we get 0.3? Once again, here is the fulcrum. The location is 0.6 meters away from this origin, and this lever arm distance here is 0.3. So we have 0.3 here, minus mass of the center of gravity, which is 10 kilograms. That's the mass of the seesaw. And it's going to be times LCOG, and that's just 1 over here, 0.1 times 0.1 meters, like that. And this should have meters. All right. We don't have to take into account the negative. The negative's already here from subtracting the other side, okay? So it's all set. And then we divide it by 30 kilograms, the mass of the little guy. So everything's been plugged in that way. And let's see what comes out. Let's see if what you predicted is true, whether or not he moves further away or closer in towards the center, all right? Let's try this out. So 50 times 0.3 minus 10 times 0.1, that's minus 1, 14 divided by 30, like this, 0.47. 0.47. So before it was 0.67, now it's only 0.47, so he's not as far. So this is 0.47 meters, that's the lever arm. So we know that position is going to be 0.9 plus this 0.47, because it's relative to this position over here, which is the pivot point, the fulcrum. So it's not 1.47, but 1.37. So this is 1.37 meters. So closer in, like that. And guess what? This part over here is exactly the same. The weights didn't change. We have the same masses for each situation over here. So adding these masses, multiplying by 9.8, the acceleration due to gravity, give us 882 newtons, just like before. So part B is no different. All we did was shift this location, but it doesn't change the mass of any of these objects, so therefore the normal force is the same. And you know what? That normal force, I just drew it in the wrong place. The normal force is actually right over here because it should be acting at the fulcrum. So I kept the drawing from before, my bad. But the normal force is actually right here at the pivot point. The center of gravity has been shifted, and so we have 882 newtons, just like before. Alrighty, that does it. Morad out.